Hey, good morning. Coming to you live here. Today, we're going to do another day of notes and we're taking a look at half-lives. Oops, I think we're on 3.3 now. Sorry about that. Half-lives. All right, here's the concept with the half-life. If I give you a radioactive nucleus, or hold on to the radioactive nucleus in your hands here, we know it's going to decay. It's radioactive. We know why it's going to decay. It's going to decay because that proton to neutron ratio is off. It does not have a 1-to-1 ratio for small atoms, less than 20, or for larger atoms, it doesn't have that 1.5-to-1 ratio, 1.5 neutrons per proton. So we know why it's going to decay. We know how it's going to decay. Alpha, beta, gamma, positron, or electron capture. So we know why, we know how. The next question is, how long? When is this radioactive nucleus in my hand going to decay? And that's a tricky question to answer. I can't tell you exactly when your radioactive nucleus, you're holding on to one too. I've got one, you've got one. I can't tell you exactly when your radioactive nucleus is going to decay. I can't. There is no measure that tells us when that'll happen. What I can tell you is if I give everyone in the classroom one, so there's 24 of us, we're all holding on to one, I can tell you when half of those will be decayed. And that is called the half-life. Now, perhaps you worked with this in algebra before. If not, it's all right. I'm going to show you how to solve these problems non-algebraically as well. But here is the algebraic expression for it. So A is the amount of substance. So again, we're all holding on to a nuclear radius, a radioactive nucleus. We're all holding on to one, and we want to know when it's going to decay. This is A sub naught. You just call it A naught. So naught's kind of like the zero there. This is how much you had at the start at time equals 0. So when you started, again, I handed everybody a radioactive nucleus at the start, time equals 0. This is how much we had. The big T, so this is raised to the power of, so it's times 1/2 raised to the power of. The big T is the total amount of time. And then the T 1/2, hopefully this one makes sense, is the length of a half-life. And the length depends on which radioactive nucleus you're working with. Some have a really, really long half-life. Some have a much, much shorter half-life. It all depends on which radioactive nucleus you're working with. All right, so for example, strontium has a half-life of 28 years. How much of a 10-gram sample is going to remain after 168 years? Well, I like to list out my variables. So A, how much? That's what we're looking for. We don't know. We want to know how much of our substance is going to be left. A naught, so how much do we have at time equals 0? We had 10 grams. Our total amount of elapsed time, 168 years. And our half-life time, 28 years. All right, so there's our variables. This one's really nice because we already have A is going to, we can solve for A, and that's what we're looking for. So it's already on the side by itself. We don't need to rearrange the equation at all. We can just say A is equal to A naught, which was 10 grams, times, now instead of hitting 1/2, I'm actually going to use 0.5. It should, hopefully we all recognize that it's the same thing. And then up to the power of, now make sure you put this in parentheses, 168 divided by 28. There we go. So that's how we're setting this up. There's our total amount of time divided by our time of a half-life. So we got 10.0 times 0.5. I'm going to use the caret button right here to go up to the power of. Now make sure you open up a parentheses. If you just type in 168, it's going to do 0.5 to the 168th power and then divide the whole thing by 28. We don't want that. We want our 168 divided by 28 all together up here. So I open and close a parentheses, hit my enter button, and there we go. The amount I expect to have left is 0.15625 grams. And with significant digits, 0.156. Kind of weird up here. We'll talk about that later in the year. But our 10 grams has 3 significant digits, so there's our significant digits. Honestly, I'm not going to stress out too much about significant digits this chapter. So there we go. After 168 years, we'd expect of our 10-gram sample to be down to 0.156 grams. So again, that's the algebraic way. And perhaps you're comfortable with that, and that's awesome. I'm actually going to recommend that you do it the non-algebraic way, which we're about to do right now. The reason why I'm going to recommend this is because we're going to graph it. We're going to graph these a lot. We're going to make a nice radioactive decay curve, and it's easier to make a graph when you have a data column. So at half-life equals 0, no time has passed. We started with 10 grams. After one half-life, 28 years will have passed, and we'll be down to only 5 grams, half of what we originally started with. That's the concept of a half-life. After a second half-life, let's see here, 28 plus 28, 56 years, we're down to 2.5 grams. So half of the 5 grams we had at this 28 interval. Third half-life, well, let's add another 28 years to that. We're up to 84 years now. Our sample size keeps decreasing by half. So we had 2.5, now we have 1.25, which is half of the 2.5. Back to how much time? After a fourth half-life, we've now gone through 112 years. Now I'm going to go ahead and use my calculator for this one. 1.25 divided by 2. I'm now down to 0.625 of a gram. Come up over here, can I continue my data column? So half-life, we're now up to 5 half-lives. The time, well, 112 plus another 28 years, one more half-life, 140 years. And the amount, 0.625 divided by 2. Now we're down to just 0.3125 of a gram. Sixth half-life, aha, there we go. Now we're up to our 168 years. And this is what the question wanted us to go to, 168 years, 168 years. So just one more time, dividing my 0.3125 in half. And there's my 0.156 grams, just like I got up here. That's 168 years. So that's the non-algebraic way to do it. Honestly, I'm going to recommend that you do that because we're usually going to make a graph with this substance. So another example, we'll make a graph with this one. So beginning with 4,000 atoms of an unstable nuclide, how many atoms will remain after 3 half-lives? After 5? Again, we can probably solve this without a graph, but we want to get practice building a graph, so we're going to go ahead and do that. So half-life, we're going to build our data column again. Time and amount. Now they didn't actually tell us what the time was. We're going to kind of ignore that column here. Because notice they don't tell us the half-life is like 10 years or the half-life is 100 years. They don't tell us that. So we can kind of ignore the time column. I know at time equals 0, I had 4,000 atoms. After 1 half-life, I'm going to be down to 2,000 atoms. After 2 half-lives, half of 2,000 is 1,000 atoms. And there we go. There's our first answer. After 3 half-lives, I'm down to half of 1,000, which is only 500 atoms. Now again, we don't know the time. I haven't filled that in yet, but we do know our amounts. All right, they want us to go one further. Half of 500 would be 250 half-lives. And finally, up to 5 half-lives, the second part of the question, 125 atoms, since that's half of 250. All right, so as I mentioned, though, we are going to be graphing this data. And so we might as well get our practice in now. We've got our data table made. First thing, so once you get your graph kind of laid out, add a title. Now, this should be really easy. Decay of, what are we looking at? Well, this one's not as easy because we're looking at an unstable nuclide. They don't tell us which one. They usually will. But we're looking at a unstable nuclide. So just kind of give it that generic title there, unstable nuclide. On the bottom, we always put time. Now, we don't know exactly what time, so we're just going to put time in half-lives. Zero off the origin there. So after 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives, try to make sure they're roughly equally spread apart. I can tell my 3 and 4 aren't quite spread out enough, but we're pretty close. All right, up at the top, I started with 4,000 atoms, so I go ahead and put that right at the top. So we always put our amount over here. And in this case, we're working with atoms. We don't always have to be working with atoms. Could be working with a mass, with grams. Could be working with percentage. But we always put our amount, whatever that is, over here. Now let's see, what if I make 3 equal level lines and make them each 1,000? Well, there we go. Make this 0 as well. This is a good looking graph. Guys, it's common for people to look over here and say, well, I'm going to take 4,000, put it here. Good, cool, that's great. Then they say 2,000 and plot it here. Okay, not great, but okay. Then they take 1,000 and plot it here. No, all right, right there, you've made a mistake, huge mistake. Do not do that. See, my graph has equal intervals. It's 1,000 right here. That same length of graph down here is also worth 1,000. Right here, same length of graph, also worth 1,000. Those are equal intervals. This is correct. If you go 4,000 and then 2,000, guess what? That interval is worth 2,000. And then you go 2,000 down to 1,000, same interval is only worth 1,000 now. That's not good. So watch out for that. Don't do that. This is the proper way to do it. Make sure you have equal intervals. All your intervals shall be worth the same. Now let's go ahead and plot our data now. Always make sure you're circling your points. When we draw a line through them, which we will in just a second here, sometimes your points get sucked up by line. You don't see them anymore. I want to see your data points. Circle your data points. So at time equals 0 or 0 half-lives, we had 4,000. After 1 half-life, we're already down to 2,000. I might be like, well, we just lost half a graph. Yeah, we did. That's fine. That's all right. This is not wasted space. That's what this graph should look like. After a second half-life, we're down to 1,000. After a third half-life, we're down to 500. So it's only going to be halfway between the 0 and 1,000. After 4 half-lives, we're only halfway up to that dot, 250. And after our 5th half-life, only 125. So again, yeah, we're really low, but that's okay. That's what these graphs should look like. Finally, then we're going to go ahead and connect them with a nice smooth curve. And there we go. Every graph you guys do should look like this. So get the practice. If you do a straight line, if you end up with a straight line, you did something wrong. Either you've got the wrong numbers on your axis, or you just flat out did your math wrong. You should not end up with any straight lines this chapter. It should all be that nice, smooth, exponential decay curve. Got one more example for you. So this is where it's going to be beneficial. I guess we should probably answer our question here. So 125 atoms after 5 half-lives and 500 atoms after 3 half-lives. To most appropriately answer the question. All right, so this is where it's very useful to actually use the non-algebraic way. We're looking for the half-life of a radioactive element. So back to our algebraic formula, we're looking for the T1 half. So unless you know how to use a logarithm, this is going to be a difficult assignment for you to do. That's why it's beneficial. If you do know how to use a logarithm, awesome. But if not, this is why it's beneficial just to make the data column like what we have been making up here and on the previous question. So half-lives, time, and amount. All right, so half-life equals 0. Our time has not started ticking yet, so our time equals 0. Our amount, 250 grams. That's where we started. After 1 half-life, again, we don't know this time. This is actually what we're going to solve for in this one. We don't know this time. Go ahead and put X there if we'd like. We'd be down to 125 grams, half of 250. Again, we don't know how much time's passed, but we do know that it's been 1 half-life. After a second half-life, we call this 2x, we would be down to, well, let me go ahead and do that math. 125 divided by 2, 62.5. After a third half-life, again, we call this 3x now. We're going to divide this by 2 again, 31.25. And after a fourth half-life, again, we call that 4x as far as our time is concerned. Divide this by 2 again, And there we go. There's our 15.6 grams. And that's what the problem said we're going to. We started with 250 grams. We're down to 15.6. We want to solve for x. Now, here's the thing. I can actually erase the 4x. We do know the amount of time to get to 15.6 grams. They said it's down to that amount after one whole day. So go ahead and put my 1 day there. Awesome, getting our practice in graphing. So I'm doing 4 half-lives this time. Over here, we put the amount, and this time we're measuring it in grams. Oops, I forgot. As soon as you make that graph, let's title it. Let's not forget that easy point. We're looking at the decay of 1:49 p.m. So there we go. Easy point to get, easy point to miss if you forget too. So that's why I said do it right away. I forgot a few seconds there, but I did remember. So there we go. Decay of 1:49 p.m. Our maximum amount was 250 grams. We bring that all the way up to the top. Now we have to think, okay, starting at 0, going up to 250, what's a nice even interval? And I'm thinking, okay, 250, it's kind of like 25. A nice even interval going into 25 is 5. Now we're not working with 25 though, we're working with 250, so we add a 0. Instead of 5, we work with 50. So there's 50. Oops. There's 100, 150, 200. There we go. Those are nice even intervals. Again, you don't just want to plug 125 in there. You don't just want to plug in 62, because when you do that, you end up with like a gap down here that's only 15.6 big, whereas up here, that same length, that same interval on the graph is going to be worth 125. You can't do that. Make sure your intervals are all equally weighted, about 50. Not about 50, they're exactly 50. I just wish I could draw a little better spaced lines. So time equals 0. We had 250 grams. After 1 half-life, we're already down, halfway down the axis here. After a second half-life, we're down to 62.5. So that's just a little bit above the 50 there. After a third half-life, boy, we're in the 30s, just over halfway up to the first marker there. And then after 4 half-lives, boy, we're barely off the ground. Nice smooth curve. Just like this one. Guys, every graph you make should have this general shape to it. Exponential decay. You get something other than this shape, you did something wrong. Let that kind of be a warning to you. Cool, so there's our good looking graph. Last part then, we actually have to answer the question. Well, we've got 4 equal intervals, x, 2x, 3x, and 4x. And we know that at 4x, it's 1 day. So how do we figure out what x is? We divide 1 day by 4. 4 equal parts equal up to 1 day. So we have 1/4 of a day. That's going to be easier if we convert that into hours. Oops, not 1 hour. I think we're all aware that it's 24 hours. Divide that by 4, and our half-life, come back over here, boy, my paper's getting crowded. Our half-life is equal to 24 divided by 4. 6 hours is the half-life of our substance. So 6 hours. In fact, we can put that here if we'd like. After 6 hours, after 12 hours, after 18 hours, and finally our 4th half-life where we got to 15.6, 24 hours. All right, so we got some practice working with some different types of problems. Definitely making graphs. Make sure you guys are taking your time and getting those in. I think there's a couple of those on the test. So definitely a big portion of the test, working with graphs and half-lives. It's what I have for you for today. So I'll see you guys. I think we'll be back next time for our next chapter. So until then, see ya.